Yeah, thank you, Roma, for your previous presentation. Thanks, Prasanna, for the invitation to present some work here, and of course all the members of the audience for their interest. So I'll be giving you a little bit of an introduction to neural architecture search, which is an added functionality of DeepHyper. And then we'll go back to our example, the sea surface temperature forecasting example that Roma just worked through, and then see how we can use NAS, that's the short for neural architecture search, for identifying a space of or identifying multiple viable surrogate models, for example, for the forecasting task. And I believe later on this afternoon we have another follow-up hands-on session, which then uses all these discovered architectures to quantify some uncertainty in our forecast as well. So, so I like that there's a spine through this workshop that follows a common theme. Okay, so we've seen this slide before, but it's a nice reminder for the audience to recognize how many different types of choices one has to make when they are constructing a neural network for any sort of application, right? So one set of choices are, hyperparameters that go into how well your architecture is optimized. For example, the choice of the optimizer, learning rates, batch sizes, and so on and so forth. And these are generally what you might find in a classical, say, a package for optimizing, the performance of your architecture. So if you go to scikit-learn grid search, you'd have options to put these down over there, and that would essentially then perform an exhaustive grid search, which, as Prasanna said, is probably not the smartest way to do things. But on the right, we have certain design choices in architectures and neural architectures, which don't really fit into the bucket of a grid search, so to speak. So, for example, you may have you may wish to search for skip connections, and we'll talk about some examples in a bit. And you may also wish to, for example, decide to choose between the types of operations that happen through the different stages of a neural network. So rather than having simply a feed-forward neural network, you look for skips, you look for identity layers. Identity layers are layers in which nothing happens, right? You just have an identity function. You may also wish to fix some layers, right? Let's say that you want a certain layer over there and you want the architecture to be searched for across that layer. So these are things that don't fit into a grid search, right? And that's the nice thing about this particular feature of DeepHyper, which sits right in the middle over here, as you can see in the schematic, where we are able to search across neural architectures. How do we make that possible? So the idea is to basically represent a neural network as a directed acyclic graph. So of course, the space of neural architectures is infinite virtually, but we have to bound it in some sense. So the way we bound it is essentially set up this graph I mentioned with nodes and edges on it. Each node and each edge has meaning to it. So for example, on the right, you can see that at a particular node, you have a choice of operations which you can select. So these can be, for example, operations 0 through 5, so 6 operations. And each operation represents a transformation that's happening to an input tensor, right? So, so for example, for these 3 nodes over here, the 0, for example, could be do not perform any operations, so terminate this branch completely. So in some sense, if 0 is not selected, you have the possibility of a skip connection, or you have the skip connection. In the middle, you have an ID operation, which means that the input comes in, nothing happens to it, it just keeps going straight forward without any transformation. But you could also have specific to our problem, which is a time series forecasting problem. You could have multiple LSTM operations with different values of, for example, the neurons in it, right? So now you can see, you can just do a visual assessment of how many operations you end up having over here. So there's 2 here, let's say 6 and 6 and 2. So you multiply all of these 2, and this is a simplified diagram for what we will actually be searching through today. And you see that the space can get really, really large, right? So we have to also figure out a way to explore this space intelligently. And so I've kind of mentioned this over here that you add operations to the various nodes. What you can also do is you can also fix certain nodes. So for example, in this first node over here, DeepHyper lets you say that, okay, perform an LSTM operation with 16 neurons. So that, so that's a priori fixed and everything is searched around it. And of course, when you make it variable, the outer loop optimization algorithm will basically then search across these operations, right? And the edges that I mentioned are basically, pathways for information flow, pathways for tensors to flow from the input all the way through to the output, where you get your, approximation of the output. Okay. So now this may sound a little complex, but through the excellent work that Prasanna and Roma have done, this is quite easy to set up in the through the DeepHyper software. There is essentially a subclass that you have to make of the K-search space class, and we'll go through this in detail in the hands-on, where we basically have to specify this graph essentially. And the way you specify this graph is, of course, you start by defining what the input and output shapes are. So what goes in over here in the sense of, the number of outputs, the dimensionality of the inputs and the dimensionality of the outputs. After this, you basically start drawing these connections. Okay. And one way to start drawing these connections is to of course, specify variable nodes and connect them to each other. What you see in the second line over here is something that we have implemented for making skip connections possible. So over here we call these anchor points, but basically it's an array or a collection of points that we hold in memory, to which we will try to connect our skip connections to, right? So, and we will say our skip connections only go back, let's say, two nodes, two variable or constant nodes. But that can be increased or reduced depending on how complex you want your architecture to be. Okay, so having specified a number of a range of nodes to add, so we call this num layers over here, but it's not really the same as layers in a feed-forward network. You can add variable nodes and then connect variable nodes to the nodes that preceded them, right? And in addition to that connection, which is easy to understand, so the variable node is connected to the node behind it, you also add operations that potentially connected to the skip connections up to two nodes in the past, right? So why I call it potentially? Because it's an operation that is possible, but not necessarily found by the search algorithm. And so over here, the approach to connecting your nodes to each other and to skip sort of nodes in the past are through certain projection operations. As you remember, each node will change the shape of your input tensor potentially, and so when this input tensor goes ahead and connects to the next node, you need to apply some dimensionality transformation. You need to apply some linear transformations to this tensor. Actually, it could also be nonlinear depending on the activation function you choose, so that the shapes are match as you go through each node. Okay, and basically the idea is once you perform all the operations at one node stage, you connect it to the past, and then add that particular node to this collection of potential skip connection lookalikes. So I finished my job with my node, but in the future some node may wish to connect to it, so I'll just add it to this collection that I constructed. Okay, so that's how you set up your search space. And once that is done, it's very easy to construct a variety of architectures. So for example, over here, I'm just constructing the search space with this build function, and then I'm sampling the search space. Again, the API makes it very easy to do so. And as you can see from the same search space, just by randomly sampling the choice of operations that were performed, for example, at each of these nodes, you get dramatically different architectures. So I'll go from complexity from left to right. So 68,000 parameters over here, 172, 344,000. And what's changing across these is basically certain skip connections are being selected or not selected, which are causing these variations in parameters, but it's the same space. So this lets you gives you a glimpse into how complex even a simple search space definition can get in terms of the expressiveness of architectures. Why are skip connections important for our discussion? There is a nice study in this reference over here where the authors visualize the loss surface of a commonly used architecture in computer vision, the ResNet 56. On the left, you have the architecture trained without any skip connections, and you can see that the loss surface, in this case, it's sort of marginalized or visualized in only in 2 dimensions, is quite, you can say, looks like somewhere you'd hike in the Southwest, I guess, but it ends up being very difficult for your optimizer because your true global minima is somewhere over here, or that is, you can't really tell it's a global minima because you're looking at only 2 dimensions. But let's say this is a desirable place for your optimizer to be at, but you may end up stopping at multiple locations before you actually get there. But with the addition of skip connections, you can see that the loss surface has been smoothed out quite a bit. Basically, it's kind of like acting like a regularization. So your optimizer has a much nicer time in finding a desirable solution. So it's always good to search for skip connections. And like I mentioned previously, grid searches do not allow you to, codify skip connections as that easily, I guess, at least for optimization. Okay, so how do we, now I've talked about how we can sample this search space. So how do we go ahead and actually sample it intelligently? Of course, random sampling is an option, but it's not efficient. We want to make this a little smarter. And so there are various techniques for outer loop optimization. So we talked about Bayesian optimization just a while ago. And Bayesian optimization is also possible in DeepHyper for the neural architecture search. Other alternatives include reinforcement learning. So you can have an outer loop agent that actually samples architectures, obtains a reward, which is given by validation accuracy, and this reward is used to train this agent to get more intelligent at sampling architectures. Over here, we went with, or at least for the purpose of the hands-on today, we'll be discussing a genetic algorithm approach to sampling architectures. We call this aging evolution or regularized evolution. So the idea is that you initialize a bunch of architectures by using that sample function I just showed you. And these are, of course, random, so there's no intelligence involved in the first step. And then the idea is that you evaluate these architectures. Again, you can scale these out quite nicely. You can evaluate them at the same time. And when you compute their validation metrics, you can use evolutionary pressure to find better algorithms, better architectures, basically. So since each architecture can be encoded into a string, basically, or an array of choices, you can interpret that that array to be a genome, and then you can go back to all the literature in the genetic algorithm based optimization community to basically search your space more effectively. So what we do specifically in this particular approach is to randomly retain some samples of this initial population that you chose, because we have to introduce the randomness is a part of this particular algorithm, and while keeping those fixed, the rest of the architectures that are preserved in the population come from mutations of the highest accuracy network. So you've chosen a network which is which network is performed the best, and you basically perturb that network by taking one of the variable nodes and just choosing a slightly different operation. So in this particular case, we don't have the classic crossover operation where 2 high performing architectures are mated, but we do have the mutation operation. So but like I said, there are many different permutations of this general workflow that can that can yield you slightly different results. But the overall idea is having an output loop evolutionary pressure. Okay, so and this is kind of a summary of what I just mentioned. You have this iterative process for randomly preserving some samples in your population, but also making random permutations to some good architectures that were discovered in your previous iteration. And then what you do at the end of the total number of iterations that you specified, or your time runs out, is that you should select the best one, right? And the best one then becomes your, in our case, will become the surrogate for our forecast model. You may also, as Krishna and Bethany will look at today, select more than one good architecture. So as you'll see, you will discover quite a few good architectures which are all equally competent. Maybe they just differ by a few percentage points, which are excusable for your application, and then you can select several numbers of these architectures and obtain estimates of uncertainty, which are very important for scientific applications, as you imagine. Okay, so so that concludes my slides. So I have a couple of minutes before I move to the hands-on. At this point, if anybody has any questions, feel free to shoot, and I can try to answer.